All right, let's get right into it. Today, we're going to talk about a surprisingly simple, almost elegant trick that might solve one of the biggest problems holding back a genuine wonder material. We're talking about a stencil that builds itself and how it could completely change the future of electronics.
So you've probably heard about graphene, right? This stuff is incredible. It's a sheet of carbon that's only 1 atom thick, it's stronger than steel, and it conducts electricity like a champ. It could revolutionize, well, pretty much everything. But, and it's a huge but, it has this one fatal flaw that's kept it out of our computer chips.
So what is this fatal flaw? What's the big roadblock? Let's break down graphene's big problem.
Okay, think about it like a light switch. This silicon in our computer chips is what's called a semiconductor. It's a perfect switch. You can flip it on and you can flip it off. Graphene, though, in its natural state, it acts more like a metal. The switch is permanently stuck in the on position. Electricity just flows all the time and you can't stop it. For a computer transistor, which is basically just a tiny, tiny switch, being able to turn off is just as important as being able to turn on.
And hey, don't just take my word for it. The researchers in this paper put it pretty bluntly. This zero bandgap thing, as they call it, poses a major problem for its practical applications. What they're really saying is, if you don't have an off switch, you can't build a computer chip. End of story.
So, the challenge was set. The race was officially on to figure out how to give graphene that all-important off switch.
Now here's the crazy part. In theory, the solution was actually kind of simple. Scientists figured out that if you could just carve a sheet of graphene into these super-duper narrow ribbons, quantum mechanics would kick in and create the energy gap they needed. Poof, you'd have your off switch.
But, and there's always a but, right? Actually making these nanoribbons was the real nightmare. The old methods just weren't going to cut it for making things at scale. You had electron beam lithography, which is incredibly precise but also agonizingly slow and ridiculously expensive. Chemical methods gave you a tiny amount of usable product, and everything else was just way too complicated. They needed something better.
And this is where our story gets really cool. This brings us to the hero of our explainer, a brilliantly simple and clever technique that uses a stencil made of tiny little spheres.
It's called Nanosphere lithography, or NSL for short. And the idea is pretty straightforward. You use a layer of microscopic spheres that, and this is the key part, assembles itself into a perfect pattern. It basically creates its own stencil or a mask that you can use to etch patterns. It's like having a microscopic, self-organizing fishnet to spray paint through.
So how does it actually work? Well, the process itself is just beautiful in its simplicity. First, you start with a nice, clean sheet of graphene. Second, you cover it with these tiny little polystyrene spheres, and they just arrange themselves into a perfect single layer. Then, step 3, you hit it with a plasma gas, which chews away any of the graphene that isn't hiding under one of the spheres. Let's see it in action.
Here's our starting canvas. This is a super zoomed-in image of that pristine graphene sheet. It's perfectly flat, perfectly clean, ready to go.
And now for the magic. You add the nanospheres, and look at that. They just naturally pack themselves into this perfect hexagonal pattern, like a microscopic honeycomb. That right there is our self-assembled stencil. And here's the final step. Think of that oxygen plasma as a nanoscale sandblaster. It just comes in and etches away everything that's exposed, leaving only the little patches of graphene that are safely protected underneath each sphere.
So we protected these little circular spots and etched away everything else. The next step is to wash away the spheres and see what pattern is left behind. And this, my friends, is where things get really surprising.
So just take a second here. Based on everything we've just seen, what pattern would you logically expect to find on that graphene sheet?
I mean, your brain tells you it should be a polka dot pattern, right? A bunch of disconnected little circles where the spheres used to be. But look at the actual result. It's not dots at all. It's this beautiful, complex, and completely interconnected network of nanoribbons. So what on earth just happened?
Well, the secret is a little something called anisotropic etching. It's a fancy term for a simple idea. The plasma doesn't just etch straight down. It also carves a little bit sideways, right underneath the edges of the spheres. And that little bit of sideways etching is what connects all the dots, turning what should have been a useless pattern into a super useful network. And check this out. This isn't a one-trick pony. By just fiddling with the spheres, the researchers could create a whole zoo of different complex patterns. You're seeing chains, branches, even interconnected rings, all made using this one simple process. Okay, so it makes really cool patterns, but here's the million-dollar question. Does it actually solve the light switch problem? To find out, the researchers decided to test it by tuning graphene on chip.
Now this part is absolutely crucial. They didn't just do this on a loose bit of graphene. No, they built a whole electronic device first with the graphene already inside it. Then they put the stencil on and etched it right there on the chip. That let them measure the electrical changes in real time.
And here are the results. Oh man, look at this. This chart shows the on-off ratio. It's the measure of a good switch. Before they start etching, the ratio is about 1. Basically, no switch at all. It's always on. But look what happens. After just 24 seconds of etching, it jumps to about 10. We have a switch. And by 30 seconds, it hits a ratio of nearly 90. They did it. They actually made it a working switch.
Let that sink in. A nearly 90 times improvement in the quality of the switch. And they did it in just 30 seconds with a simple, self-assembling process. That is just wild.
So, let's just recap why this is such a potential game changer. The NSL advantage. It's low cost. You're using cheap little plastic spheres. It's high throughput because you're patterning the whole area at once. It's scalable, meaning you could do this on big industry standard wafers. And maybe best of all, it's simple and it's fast. It's just elegant.
Which brings us right back to our big question. We had a massive, complex problem holding back a revolutionary material, and the solution might just be this incredibly simple, self-assembling stencil. So you have to wonder, could this little trick be the key that finally unlocks the door to the next generation of super-fast, super-efficient electronics made from graphene?